Hello, AP Statistics students, Mr. Eicher here. We're talking about an exam from way back when, 2006, Form B, and it was question number 3, affectionately known as the Iron Byron, since the Iron Byron right there is mentioned. I'll assume that you've already read the question. Important information to be able to answer part A. Particular, the last second to last sentence, particular manufacturer determined the distances traveled for the golf balls are normally distributed and a standard deviation of 2.8, and they want the golf ball not to exceed 291.2 to be able to be a regulation golf ball, I guess. This manufacturer has a new process that allows it to set the mean distance the ball will travel. So part A, if the manufacturer sets the mean distance to 188, so that's our mean, what is the probability a ball that is randomly tested will travel too far? So too far is anything exceeding 291.2. So we'd like to know the probability that the distance, let D be the distance the ball traveled, that D is greater than 291.2. Well, we're told that we have a normal distribution with 288 as the mean, and the standard deviation was given as 2.8. So that would give us a normal curve with a center of 288, a standard deviation of 2.8. And 291.2 is looks maybe about close to 1 standard deviation. That or more, anything up here would be not regulation. The direction is greater than, so we shade to the right of our boundary, which is 291.2. So to calculate, I encourage my students to find z-scores. So to convert, we would take our boundary, 291.2, minus our mean, 288, and divide by 2.8. And that would give us 1.14 is our z-score. So we're looking for the probability that a z-score in a normal curve would be greater than 1.14. If you're going to use this probability notation, be careful to use it right. You don't want to lose credit on the AP exam because you've used the notation incorrectly. So to find this, we could then type it into our calculator, normal CDF. Normal CDF, our lower bound. If you're just going to not type the z-score in there, your lower bound would be 291.2. Your upper bound would be infinity, or 9999999. Your mean would be 288. And your standard deviation would be 2.8. Or that would look kind of like this. Second vars, normal CDF, number 2. The lower bound was 291.2. Your upper bound is infinity, some large number. Your mean, it was the Iron Byron was set to 288 yards, and then 2.8 yards. So if they set the mean to be 288, there is a 12.7% chance that the golf balls will not be made to the correct standard. That was part A. So we're going back here. So this answer, this shaded region right there, is 12.7%. It asks for a probability, so I guess technically it'd be a number between 0 and 1. So 0.127 would be the answer to A. You do have to show work. If you're going to use the normal CDF, make sure you label the lower bound, upper bound, mean, and standard deviation. But as you know, if you're my student, I love the z-score. So including the z-score can help you out. But you definitely want to either use the normal CDF commands, make sure you do like a well-labeled sketch, because part of your score will be based on communication, and showing your work is part of that communication process. Let's look at question B. I believe we're going to have to remember this number though. So 127.127. I think we're going to need that on question B. So let's take a look at question B. Question B says, assume the mean distance traveled is 288 yards. Okay, that's the same as above. And that 5 balls are independently tested. What is the probability that at least one of the 5 balls will exceed the maximum distance of 291.2? So we're looking for what is the probability at least one of the 5 exceeds. I like to write it like this because this at least 1 out of 5, that is an indication that I should be thinking this might be a binomial probability. It's binomial because we have B for bins. We have success and failure. Success is, I guess, exceeding. And then we have failure, which is not exceeding. We have they are independently tested. We're told right there they're independently tested. So there is independence. So we're told about that. And then we have a fixed number of trials. They're going to hit 5 golf balls. That was that, number 5. And then we have the same probability of success, which the probability that one of the balls exceeds the 291.2. That probability we got from part A. That probability was the 127 from part A. So we'll look at 2 approaches to do this. One approach is let's use the complement. So the probability at least 1, well, that would be the same as the probability of 2 or 3. At least 1. I'd better start with 1. 1 or 2 or 3 or 4 or 5. That's a lot of probabilities we'd have to calculate. So instead we'll do the complement. The only other case that isn't addressed there is the probability of 0 exceed. So to calculate this, we'd have 1 minus the probability 0 exceed out of 5. That would be there 5. You're choosing 0 to exceed. The probability that it exceeds is 0.127 to the 0. And the probability that it doesn't exceed is, let's see, the complement of 127 is 873, I believe, to the 5. So if we calculate that, that would give us, that whole thing would give us the probability that at least 1 exceeds. So to see what that looks like on the calculator, we would have 1 minus the probability of 5 choose, under probability, 5 choose 0, parenthesis, 0.127 raised to the 0, and then the complement of that, just to make sure I don't type it wrong, I'll just ask the calculator to calculate 1 minus 0.127 raised to the 5. And we get an answer of at least 1 exceeding the standard would be 0.493. would be our answer to B. Another approach that you could take, we could, instead of using this whole formula here, the binomial theorem, you could do binomial PDF. Well, I guess you could do CDF. It's at least one, but they're going to give equivalent answers. So if we did CDF, we have 5 trials. We have a probability of exceeding the standard of 0.127, and our x value is actually going to be 0. If we want at least 1, the complement would be 0, and we'd paste that in there. And we get this answer, which, wait a second, that's not the same as this. What's wrong? Well, this is the probability you get 0 or less, which is just 0 in this context. So we have to do the complement of this, 1 minus that previous answer. And now the answers are the same, 493, and that's what we got doing this way, 493. In this context, you would be able to do binom PDF or CDF because either one is going to give the same answer since we only have one case, which is the 0th case. So that's our answer, 0.493 for part B. So that's what we had, 0.493, 0.493. So the probability at least one exceeds is 0.493. I would warn you, if you're going to use the calculator function and write it like this, 1 minus binom CDF, again, you have to label n is 5. Your probability is 0.127, and then x is 0. And you're doing the complement. I do want to point out on this one, we actually had 2 complements. We had this complement here, the 1 minus the probability, to find the complement of at least 1 out of the 5. But we also had this complement, which is built in to the binomial theorem. The complement of 0.127 is 0.873. Now this formula, last thing then we'll move on, this formula right here, get rid of all this around it, that formula right there could be simplified. So maybe you looked at the answer key and they just had something like this. Or maybe even they had something like this with a lot of 1 minuses in there. This, you could see that we're using 2 complements. This formula right here, 5 choose 0 is 1, so we don't really need that. And then 0.127 to the 0, that's 1, so we don't really need that. So that would simplify to be 1 minus this amount, which I wrote right here. But that 0.873 came from 1 minus 0.127. So either way you can show your answer, but I'd like to show it with this binomial theorem right here. Just to review the binomial theorem. Okay, that's enough for that, and let's look at part C. Part C says if the manufacturer wants to be 99% certain that a randomly selected ball will not exceed the maximum distance of that, what is the largest mean that can be used in the manufacturing process? Remember earlier we had said in part A and B, we were assuming that they're using a mean of 288. And then in part A, our answer was pretty big. It seemed like pretty likely that they're going to exceed the standard with setting it at 288. So let's just start with a picture. We have a normal distribution. We're told in A that these are normally distributed. And we don't know the mean. We still have the standard deviation is 2.8. That was told above. We want to be 99% certain that it doesn't exceed 291. So 291 should be like way out here in the tail, 291.1. And this 99%, that is basically implying that we want 99% of the distances to be less than that 291. So we want the probability that the distance is less than 291.2. We want that probability to be 99.99 or 99% certain. So in this one, we're not told the mean, and we're given a percentile, basically, the 99th percentile. So to calculate this, this is one of those delightful questions that students who might think, oh, you know what, I'm going to use inverse norm. Yeah, inverse norm. And I'm going to put the area as 0.99. The mean, well, I don't know. The standard deviation is 2.8. Uh-oh, what do I do? How do I do this? Because I don't know the mean. Darn test development committee people writing questions that make my tool backfire. Well, using inverse norm is a fantastic idea, but I would encourage you, you can always use inverse norm. You can always use inverse norm to find a z-score. So let's convert this boundary to a z-score using inverse norm. So inverse norm gives z-scores. Our area is 0.99. Our mean with z-scores, we always know the mean of a z-score is, a z-score distribution is 0. And the standard deviation of a z-score distribution is always 1. And those are really, really helpful tips there. If you're not sure in a normal distribution what the mean and standard deviation are, convert it to a z-score first. So when we do that, then we're going to be able to use our z-score formula, which is this. And we're going to find that z-score with that formula. We know the boundary, which is 291.2, and we know the standard deviation, which is 2.8. And then we'll be able to solve for mu. So let's see if I could remember all those steps looking at my calculator here. So the calculator, we need to do inverse norm, second vars, number 3, inverse norm of 0.99. And it's the tail on the left. I got a fancy calculator now. So that's our z-score. That z-score, we're going to have our z-score, our z-score 2.326 equals our boundary 291.2 minus the mean all over the standard deviation, which was 2.8. So solving that, multiply both sides by 2.8, do a little algebra, get that over there, and then solve. So that's going to be that answer times 2.8. Enter. And then let's see, if I add the mean over and then subtract this, I think that would be 291.2. That's our boundary, right? 291.2, yeah. And then minus this answer. And we get the maximum that the mean should be set to be within standard is 284.69 yards is what our mean needs to equal. That makes sense in the context. If you remember part A, when it was the mean was set to 288, we had a very high probability. I think the probability, I mean it's not that high, but we had a probability of about 13% that we would exceed. Whereas if we set the mean lower, since the mean's set lower, it's not going to go as far. So now there's only a 1% chance that we exceed the standard. And the company would probably want that. Like, they don't want to make a bunch of golf balls that 13% of the golf balls aren't regulation golf balls. They're finding it acceptable to have 1% of golf balls not be in regulation. Maybe they would want it to be even a smaller percentage. But that was part C, 284.7 yards. Thanks for watching this video.